First, we'll draw our cube so that we can identify the correct vertices. A and C are diagonals, so I'll put A over here and C over here. AB is parallel to CD. Let's take a view of our cube and rectangle ABDC with respect to the plane, looking edge on from the plane. Vertex A is on the plane and B is 2 above it. And then we have this rectangle. We'll draw these perpendiculars from B and C. This distance is 2. C is 8 meters above the plane, so we'll call that 8. Since AB is the side length of the cube, we'll call it S. And since AC is a diagonal, that makes this length S root 2. When we identify congruent angles, we see we have a pair of similar triangles. I'll label these points E and F. And we have triangle CEA is similar to triangle AFB, and we'll fill in some of these lengths. Find the ratio of corresponding sides and solve for S. So we have the side length of our cube is 6. We are also given that our rectangle ABDC is perpendicular to our plane, which means it's contained within a larger plane that's also perpendicular to P. Since this plane is perpendicular to P and AC is a diagonal, then if we think about where the other two vertices of this square, let's call them P and Q, we're going to see that the distance from point P and point Q to plane P is going to be the same. In other words, this cube is not going to lean to the left or the right with respect to the diagonal AC, or BD for that matter. So when we look again from the edge of plane P, straight on to the face, APCQ, we have A is on the plane, C is above it, and P and Q both going to be the same distance from the plane. C will not be directly above A. If A is in the plane of this whiteboard, then C is in front of the plane of the whiteboard. But what this means is when we fill up this cube with water, if the edge of the water on this square is GH, then we have that GH is parallel to QP, and we have triangle CGH is an isosceles right triangle. We're going to see something similar on the other side of our cube at the square with diagonal BD. When we fill it up with water, our water line is going to be a little bit further below D because it's tilted up here. Let's call this water line RL, and we're also going to have a right triangle that's isosceles D, R, and L. Let's try to draw our cube again. And I'll draw in the water line. This is G and H and R and L in the back. It looks like rather than finding the volume of the water, it'll be easier for us to find the volume of the air above contained in this frustrum between triangles CGH and DRL. Again, CD is the side length of our cube, so it has length 6. We should be able to extend CD, HL, and RG. We'll call this point where they meet S. This distance is 6. Let's find the dimensions of these two isosceles right triangles. Again, we'll take an edge-on view of the plane and rectangle ABDC. Here is our water line, and I'm going to draw some of these perpendiculars again. Our water line is 7 meters above the plane. Since CE is 8, this distance here is 1. Let's draw this altitude from C to this triangle, and we'll call this point J. In our diagram over here, J is this point. J is 1/8 of the way from C to A, and CA is the diagonal of one of our squares. So CJ is 3 root 2 over 4. That's the height of our isosceles right triangle. EF is 2. If we call this point L, since D is 10 units above the plane, DL has length 8. If we call this point M, DM is 3 and ML is 5. When we draw an altitude from vertex D down to RL, we'll call this altitude DK. And this is K here on this diagram. K is 3/8 of the way from D to B. And DB again is a diagonal. So the height of our other isosceles right triangle is 9 root 2 over 4. These two pyramids, SCGH and SDRL, are essentially similar to each other. Corresponding linear measurements, CJ and DK, which are the heights of the triangles that serve as the bases, they are in a ratio of 1 to 3, which means the corresponding volumes is going to be the cube of this linear dimension, or 1 over 27, which means the volume of our frustrum between these two triangles is going to represent 26 over 27 of the volume of our big pyramid, SDRL. All we need to do now is find the height of this big pyramid, where CD is equal to 6. Since the linear measurements of these two triangles are in a ratio of 1 to 3, the heights are also in a ratio of 1 to 3. This is satisfied when CS is 3 and SD is 9. So we'll use our formula for the volume of a pyramid. That's 1/3 base times height. Our base is going to be the area of triangle DRL, and our height is going to be SD. DRL is an isosceles right triangle with height 9√2/4. So the area of this triangle is the square of that. 81 times 2 over 16, and we multiply this by 9. We'll cancel out factors in the numerator and denominator, and we're left with 13 times 9 over 4. This is 117 over 4, and again, this is the volume of the air inside the cube. To find the volume of the water, we subtract this from the volume of the cube. Our answer is 747 over 4. We are asked for the sum of the numerator and denominator, which is 751. If you'd like me to solve any other contest problems, please leave them in the comments.